students. Today we're going to talk about the families and properties of the periodic table. By the end of this video, you will be exactly as cool as Freddie here, or at least you will understand what this picture means. So, first family, the hydrogen family. It's pretty brief. It's just hydrogen. It's represented by the symbol H, and it has the electron configuration of 1s1. We're actually not going to go through the electron configurations of all the rest of them, but since there's just this one atom here, we can do that. It's colorless, odorless, and tasteless gas. It forms compounds, more compounds than any other element, very, very common. And it's the most abundant element in the universe. Kind of convenient. There's very little free hydrogen in the Earth's atmosphere. It mostly is diatomic gas. Remember, diatomic means there's two hydrogens together. And again, that's because it wants those two valence electrons. It's going to share those, and thusly we get hydrogen gas. It has the lowest density of all gases at room temperature and pressure, and it is flammable, actually highly flammable. Hydrogen gas. Now, the alkali metals. I want to point out, first of all, it does not have hydrogen in it. Hydrogen is not a metal. It is a non-metal. But the alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. They do not occur in nature as elements by themselves. Some people know you can get them, but they don't occur naturally in nature. They usually occur as a white salt compound with something else. And that's because they're very, very reactive. They really, really want to get rid of that one valence electron. In fact, they're super reactive with water. Again, one valence electron there in group 1. We know all elements in group 1 have one valence electron. And they're good conductors of heat and electricity. They're ductile, they're malleable. Ductile, they can be made into wires. Malleable, they can be bent. And they're soft enough to be cut with a knife. And they also have a silvery luster, low density, and a low melting point. That's what MP means, not military police. Alkaline earth metals. These are group 2, the boys next door. I guess they could be girls too. Interesting. Anyway, they're made up of beryllium, magnesium, calcium, strontium, barium, and radium. Right down the list, radium is pretty rad. It's also my favorite atomic number. Do not occur naturally in their elemental state. Again, they're usually a salt. They're two valence electrons. Remember, group 2, two valence electrons. They're less reactive than alkali metals. Remember, if you only have one to get rid of, you really want to get rid of it. If you have two to get rid of, you're a little less likely to get rid of them, but they're still reactive. And they're good conductors of heat and electricity. Again, they're ductile and malleable, and they have a silvery luster. Now into the transition metals. There's a lot of them. I am not going to go through all of them. Some of my favorites are gold and platinum, and I guess you could probably guess why. But mercury's in there, and so is zinc and copper and nickel and cobalt and iron. There's a lot of them. They're all metals. They contain one or two valence electrons, but again, there's not a nice pattern to follow, so we don't give you a nice pattern there. They're usually harder and more brittle than metals in groups 1 and 2. They have a higher melting point and boiling point than metals in groups 1 and 2. They're still malleable and ductile, and they have a silvery luster except copper and gold, because copper is copper-colored and gold is gold-colored. More about transition metals. They include radioactive elements with numbers 89 through 118. They include the only liquid metal at room temperature, which is mercury, just like our friend Freddie. And they tend to have two or more common oxidation states. We'll get more into that later, but know that they have two or more common oxidation states. Into the inner transition metals, the lanthanides and the actinides. I will say these. There is lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium. Those are the lanthanides. And then there's actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, and nobelium. Some of these are going to be things that you recognize, and that's what they're named after, but that's just a quick little lanthanides and actinides. The lanthanides, they're shiny silvery metals in reactivity similar to group 2. Again, not as reactive as group 1, but similar to group 2. And the actinides down below, they're all radioactive. Remember, radioactivity is just an unstable nucleus that has a tendency to break down and give off gamma rays and those alpha and beta particles. And 3 were found on Earth. The rest were man-made. So keep this in mind. A lot of these elements were just made in a lab, because we can do that now. That's how we discover new elements, actually, is we make them. The Boron Family. Boron, aluminum, gallium, indium, thallium, and I'm not going to say these ones. Their names actually mean just the number. Ununtrium is it means 113, and it's just a placeholder. They will eventually get names as we discover them and name them. It's a long, complicated process. You guys will see atoms get named in your lifetime, definitely, as we discover them, but they don't really have names just yet. They do not occur in the elemental form except for aluminum, which is the most abundant metallic element. It's very, very common in nature. The rest are scarce in nature. They have 3 valence electrons. Remember, group 13, we can get rid of that 1, and we just have the 3, or subtract off 10. They are metallic solids except for boron, which is a solid metalloid. And all are soft and have low melting points. It doesn't take much heat in order to get them to become liquid, except for boron, which is hard and has a high melting point. Again, as we get into these last groups here, there's going to be a division with that staircase. And they're chemically reactive at moderate temperatures, again, except for boron. Carbon family. It's carbon, silicon, germanium, tin, and lead. It includes a nonmetal, carbon, 2 metalloids, silicon and germanium, and 2 metals, tin and lead, which 2 symbols that seem very silly, but again were named a long time before we had the English names for them. That's why SN and plumbum, I know, was the name for lead. They vary greatly in both physical and chemical properties. This one, because there's nonmetals, metalloids, and metals in it, it's very different as you go down the group. They occur in nature in both combined and elemental forms, and they have 4 valence electrons. They are relatively unreactive relative to other elements. Group 15, the nitrogen family, is nitrogen, phosphorus, arsenic, antimony, and bismuth. It consists of 2 nonmetals, nitrogen and phosphorus, 2 metalloids, arsenic and antimony, and 1 metal, bismuth. They range from very abundant elements, nitrogen and phosphorus, to relatively rare, arsenic, antimony, and bismuth. Again, antimony, very, very difficult to look here and get antimony from it, something you just got to know. And they contain 5 valence electrons, again, group 15. Oxygen family. This is oxygen, sulfur, selenium, tellurium, and polonium. They occur naturally as elements and in combined states. They consist of 3 nonmetals, oxygen, sulfur, and selenium, and 1 metalloid, tellurium, and 1 metal, polonium. They have 6 valence electrons, and they tend to exist as diatomic and polyatomic molecules. Interestingly, you get oxygen gas, but you also get ozone, O3, and then you get sulfur 6, sulfur 8, and selenium 8. Now on to the halogens. They've got fluorine, chlorine, bromine, iodine, astatine. All are nonmetals. All are found in the rocks of Earth's crust and dissolved in seawater. And they exist in room temperature as a gas, fluorine, chlorine, as a liquid, bromine. Again, bromine is the other liquid, just like mercury at room temperature and 0 degrees Celsius, STP. And as a solid, iodine and astatine are a solid down here. And they all have 7 valence electrons. And because they have 7, they're so close to that 8 that they want that 1 valence electron to form the ions, and they're highly, highly reactive. On to the noble gases. All of them have a full valence shell, including helium, even though it only has 2 electrons. And it's helium, neon, argon, krypton, xenon, and radon. They're in minute quantities in the atmosphere. Helium can be found from natural gas wells where it's accumulated, because radioactive elements, they will break down and they will break down and they will break down and they will break down until they eventually become helium, a really small element with only 2 protons and 2 neutrons. And it also has 8 valence electrons again, except for helium, which only has 2. But they're all relatively non-reactive relative to all the other elements. All gases are monatomic. They don't even want to react with themselves. They're loners. Originally, they were just called the inert gas because it was thought that they formed no compounds, but over time and with greater technology, we figured out that some of them do. Again, unreactive, they have closed shell, but krypton will react with fluorine to form KrF2, and actually xenon will form several compounds with oxygen and fluorine as well. It's not going to be like a halogen reaction. It's not going to be an alkali-earth reaction. You really have to try to make these compounds, but because they are pretty comfortable in their full valence shells, non-reactive. And those are the groups and families of the periodic table. Hopefully you enjoyed yourself.